Hello, and welcome to General Astronomy, Lecture 28, The Fate of High-Mass Stars. Human life would be impossible without both low and high-mass stars. The long lives of low-mass stars allow evolution to proceed for billions of years, but only high-mass stars produce the full array of elements on which life depends. The early stages of a high-mass star's life are similar to the early stages of the Sun's life, except that they proceed much more rapidly. But the late stages of life are quite different for high-mass stars. Like all other stars, a high-mass star forms out of a cloud fragment that gravity forces to contract into a protostar. Just as in a low-mass star, hydrogen fusion begins when the gravitational potential energy released by the contracting protostar makes the core hot enough. However, hydrogen fusion proceeds through a different set of steps inside high-mass stars, which is part of the reason that these stars live such brief but brilliant lives. A low-mass star, like our Sun, fuses hydrogen into helium through the proton-proton chain. In high-mass stars, however, the strong gravity compresses the hydrogen core to a higher temperature than we find in lower-mass stars. The hotter core temperature makes it possible for protons to slam into carbon, oxygen, and nitrogen nuclei, as well as into other protons. So it's not just the proton-proton chain working anymore. Protons can collide with other elements. So we have a new cycle of reactions. The carbon, nitrogen, and oxygen act as catalysts for hydrogen fusion, making it proceed at a far higher rate than would be possible by the proton-proton chain alone. This faster chain of hydrogen fusion reactions is called the CNO cycle, with the letters C, N, and O standing for carbon, nitrogen, and oxygen. So this diagram here illustrates the 6 steps of the CNO cycle by which massive stars fuse hydrogen into helium. The overall result is the same as that of the proton-proton chain. As you see in the middle, 4 hydrogen nuclei fuse to make 1 helium nucleus. The carbon, nitrogen, and oxygen nuclei are simply catalysts that help the cycle proceed, but are neither consumed nor created in the overall cycle. So you can see, for example, maybe a carbon will slam into a free proton to create nitrogen, but then that will decay into carbon again, which will slam into another, and this is carbon-13 by the way, will slam into another proton to create nitrogen-14, and then another proton to create oxygen, and so on and so forth. The overall reaction, though, is the same as the proton-proton chain was for stars like our Sun. It just occurs more rapidly now because there's other things that can help drive this process. The end result, though, to get our helium is when you have nitrogen-15 colliding with another proton that decays and splits into a helium and a carbon again, and then the process just cycles. That's why this is in a circular pattern. During the entire lifetime of a low-mass red dwarf star with an initial mass less than about 0.4 solar masses, the only nuclear reactions that take place is the fusion of hydrogen nuclei to form helium. In stars with initial masses from about 0.4 to 4 solar masses, a second kind of nuclear reaction takes place, helium fusion, as we've discussed. The heaviest elements manufactured by helium fusion are carbon and oxygen. These stars cannot make elements heavier than carbon because degeneracy pressure halts the contraction of the core before it can get hot enough for fusion. A high-mass star has no such problem. The life story of a high-mass star with a main sequence mass greater than about 4 solar masses begins with these same reactions, that being hydrogen and then helium fusion. But calculations show that high-mass stars can also go through several additional stages of nuclear reactions involving the fusion of carbon, oxygen, and other heavy nuclei. As a result, high-mass stars end their lives quite differently from low-mass stars. Let us consider how the late stages in the evolution of a high-mass star differ from those of a low-mass star. In low-mass stars, as we saw previously, fusion stops in the carbon-oxygen core. It eventually becomes a white dwarf. But in stars whose overall mass is more than about 4 solar masses, the temperature and pressure of the carbon core is hot enough to trigger further fusion reactions. The first of the nuclear reactions is carbon fusion, which consumes carbon and produces oxygen, neon, sodium, and magnesium. If a star has an even larger main sequence mass of about 8 solar masses, even more nuclear reactions can take place. After the cessation of carbon fusion, the core will again contract, and the star's central temperature will exceed 1 billion degrees Kelvin. It is around this temperature that neon fusion begins. This uses up the neon accumulated from carbon fusion and further increases the amount of oxygen and magnesium in the core. After neon fusion ends, the core will again contract, and oxygen fusion will begin. The principal product of oxygen fusion is silicon. Once oxygen fusion is over, the core will contract yet again. With this contraction, the central temperature rises and silicon fusion begins, producing a variety of nuclei from sulfur to iron to nickel. While all of this fusion is going on in the star's interior, at the surface the star is losing mass at a rapid rate. Each stage of nuclear reactions in a high-mass star helps to trigger the succeeding stage. In each stage, when the star exhausts a given type of nuclear fuel in its core, gravitational contraction takes the core to an even higher density and temperature, thereby igniting the, quote, ash of the previous fusion stage, and possibly the outer lying shell of unburned fuel as well. The increasing density and temperature of the core make each successive nuclear reaction more rapid than the one that preceded it. As an example, this table shows a theoretical calculation of the evolutionary stages for a star with an initial main sequence mass of 25 solar masses, so a star 25 times the mass of our Sun. So notice, as even a star like our Sun does, it goes through hydrogen fusion and it will go through helium fusion. But a star like our Sun of 1 solar mass ends with helium fusion when carbon is produced in the core. But these more massive stars can produce lots of different types of fusion. So notice the required temperature increases for each, along with the density. But notice that the time or duration of each stage goes down quite significantly. In fact, the last type of fusion in this type of star, silicon fusion, it only lasts for 5 days compared to, 10 million years of hydrogen fusion? So this is really quite impressive how quickly these things can change. Now that we know that there's all these different types of fusion, let's take a look briefly at the structure of such a star. Each stage of core fusion in a high-mass star generates a new shell of material around the core. After several such stages, the internal structure of a truly massive star, say maybe 25 to 30 solar masses or greater, resembles that of an onion, with layer upon layer of shells fusing different elements. Notice the order of the layers in the figure. The earlier the fusion reaction begins, the farther it is from the center. Because nuclear reactions can take place simultaneously in several shells, energy is released at such a rapid rate that the star's outer layers are expanding tremendously. The result is a supergiant star, whose luminosity and radius are much larger than those of a giant. The star's overall size can be as large as Jupiter's orbit around the Sun. Despite the dramatic events taking place in its interior, the high-mass star's outer appearance changes slowly. As each stage of core fusion ceases, fusion in the surrounding shell intensifies and further inflates the star's outer layers. Each time the core flares up, the outer layers contract somewhat, but the star's overall luminosity remains about the same. The result is that the star's life track zigzags across the top of the HR diagram. In the most massive stars, the core changes happen so quickly that the outer layers don't even have time to respond, and so the star progresses fairly steadily toward becoming a red supergiant. So you can see how it comes almost straight off of the HR diagram. It doesn't even have time for the outer edges of the star to react to what's going on in the core, so it just progresses straight over. So this just shows you the quick evolutionary tracks of such stars. A supergiant star cannot keep adding shells to its onion structure forever, because the sequence of nuclear fusion reactions cannot go on indefinitely. In order for atoms to serve as nuclear fuel, energy must be given off when they collide and fuse. To act as a fuel, nuclear fusion reactions must release energy. This is the energy that powers a star. As larger and larger atoms are built up inside of a star's core, they will eventually approach a size where they can no longer release energy through fusion and would instead require an input of energy in order to fuse. At this point, the star has run out of nuclear fuel in its core. Iron, is the first atom produced for which further fusion does not release energy. In fact, iron is unique in a very important way. It is the one element from which it is not possible to generate any kind of nuclear energy. Iron has the lowest mass per nuclear particle of all nuclei, and therefore cannot release energy by either fusion or fission. Once the matter in a stellar core turns to iron, it can generate no further energy. The core's only hope of resisting the crush of gravity lies with degeneracy pressure, but the iron keeps piling up until even degeneracy pressure cannot support it. What ensues is the ultimate nuclear waste catastrophe. The star explodes as a supernova, scattering all the newly made elements into interstellar space. Our present understanding is that stars of about 8 solar masses or less shed most of their mass in the form of planetary nebula. The burnt-out core that remains settles down to become a white dwarf. But the truly massive stars, the stellar heavyweights that begin their lives with a mass of more than 8 solar masses of material, do not pass through the planetary nebula phase. The core of an aging massive star gets progressively hotter as it contracts and ignites successive stages of nuclear fusion. But even as more of the star's core is converted into iron, this iron is unable to undergo further fusion. Without this heat-producing nuclear energy, the usual pressure that supports the star from collapse is now absent. Nonetheless, the core is held up briefly by degenerate electron pressure, which is the same pressure that keeps a white dwarf from collapsing. However, degenerate electron pressure can only hold up to 1.4 solar masses against its own tremendous inward gravitational pull. When enough iron builds up to cross this threshold of mass, the result is a cataclysmic core collapse. The collapse is so sudden and gravity is so strong that the outer core comes rushing in at over 20% the speed of light. Even though steady fusion reactions in the core end with iron, the collapsing core soars in temperature due to the gravitational implosion. Temperatures skyrocket to about 10 billion degrees Kelvin within a fraction of a second. As a result, gamma-ray photons emitted by the insanely hot core have so much energy that when they collide with the iron nuclei, they begin to break the iron nuclei down into smaller helium nuclei. This is a process known as photodisintegration. It takes a high-mass star millions of years and several stages of nuclear reactions to build up an iron core, but within a fraction of a second, photodisintegration blasts apart much of that core. Within another fraction of a second, the core becomes so dense that the negatively charged electrons within it are forced to combine with the positively charged protons to produce neutrons. In fact, most of the core is converted into neutrons. This process also releases a flood of neutrinos, denoted by the Greek letter nu, that is the curly V. There are other processes that produce neutrinos as well, and because these neutrinos carry away a substantial amount of energy from the core cools down and condenses even further. At about 0.25 seconds, that is a quarter of a second, after its rapid contraction begins, the core is less than 20 kilometers in diameter and its density exceeds 4 times 10 to the 17 kilograms per meter cubed. This is nuclear density, the density with which neutrons and protons are packed together inside nuclei. If Earth were compressed to this density, it would only be about 1,000 feet in diameter. Matter at nuclear density or higher is extraordinarily difficult to compress. Just as compressed electrons experience degenerate electron pressure, these neutrons in the core attain a degenerate neutron pressure. Thus, when the density of the neutron-rich core begins to exceed this nuclear density, the core suddenly becomes very stiff and rigid. The core's contraction comes to a sudden halt, and the inner part of the core actually bounces back and expands. This core bounce sends a powerful shockwave of pressure, like an unimaginably intense sound wave, outward into the outer core. So you have matter just rushing down really quickly, but that core suddenly solidifies and everything bounces off of it. That's called the core bounce. Initially, it was thought that the core bounce was sufficient to generate a shockwave that propelled a star's matter outward during a supernova explosion. While there is evidence for a shock wave, more energy is needed than can be provided by the core bounce alone. One of the mechanisms that can produce additional energy to the shock wave appears to involve those neutrinos. At first glance, you might not expect neutrinos to have an explosive effect because they interact so weakly with matter. Recall that after a trillion or so neutrinos pass through your head each second, which is our sun's normal output, most of them pass right through the Earth without even getting absorbed. In a collapsing core, however, the density of matter is so high during the collapse that even neutrinos are absorbed to significantly heat the matter around the core. These neutrinos are essential to what follows. The absorbed neutrinos are thought to carry enough energy to produce hot, inflating bubbles. As the outer boundary of these bubbles pushes on matter around the core, the resulting shock wave ejects material from the star altogether. The result is an explosive supernova. When the shock wave breaks out of the star, portions of the explosive energy escapes in a torrent of light. At this point, the star has become a supernova, or plural is supernovae. Specifically, what we have described is the formation of a core collapse supernova. Note that we give it a specific title, core collapse supernova, because there are other ways to produce them. So this here is just a summary of what we've discussed so far. One way to think about the evolution of a massive star's core is that it undergoes an unrelenting gravitational contraction. Before the star arrives on the main sequence, hydrogen contracts until hydrogen fusion produces enough heat and pressure to temporarily halt further contraction. But as the resulting helium builds up, the core contracts until helium fusion turns on and produces a temporary halt to further contraction. This pattern continues all the way through the production of iron in the core, with each stage of fusion, or each onion layer, providing only a pause in the unrelenting contraction. But these pauses in gravitational contraction require pressure that was produced by the release of nuclear energy. While that was possible when fusing elements lighter than iron, the iron core does not release nuclear energy and offers nothing to support the surrounding layers against gravity. With nothing to hold off gravity, the surrounding layers rush inward, gaining tremendous speed and energy. The core is also compressed further as a variety of processes unfold. However, more than anything else, the energy of the infalling matter is ultimately converted into neutrinos. In this sense, a supernova can be seen as a gravity-powered neutrino explosion. For a few seconds during the collapse, the neutrino energy output is unimaginably intense. While a supernova can outshine an entire galaxy with its visible light, the energy in neutrinos is 100 times greater. By depositing only a tiny fraction of this energy in surrounding layers of the star, the neutrinos produce hot inflating bubbles that propel most of the star's matter into space. Detailed computer calculations suggest that a 25 solar mass star ejects about 96% of its material into the interstellar medium for use in producing future generations of stars. Less massive stars eject a smaller percentage of their mass into space when they become core collapse supernova. Before this material is ejected into space, it is compressed so much that a new wave of nuclear reactions sets in. These reactions produce many of the atoms on the periodic table of the elements that are heavier than iron. Reactions producing the heavier elements require a tremendous input of energy, and thus cannot take place during the star's pre-supernova lifetime. Hence, much of the heavy element materials that make up our solar system, Earth, and even our bodies were only possible to be produced in violent explosive supernova. Basically, anything over iron had to come from a supernova explosion. So that's really something to think about. All the gold, all the silver, all that stuff, that only came from supernova explosions. So I did mention that there were other types of supernovae, so we'll get into that a bit here in the next couple slides. There are two main mechanisms for a supernova explosion. We have already discussed one mechanism, the core collapse supernova. A second mechanism involves at least one white dwarf star in a binary star system. That means where two stars are orbiting one another. The first indication that there were different types of supernova came from their different spectral lines. As a result, supernova are labeled not by their underlying mechanism, but by their spectra. Supernova with hydrogen emission lines are called type 2 supernova. These are core collapse supernovas of the sort that we've just described. So core collapse supernovas are called type 2 supernovas. They are caused by the deaths of highly evolved massive stars that still have an ample amount of hydrogen in their atmosphere when they explode. When the star explodes, the hydrogen atoms are excited and glow prominently, producing the hydrogen emission lines that define type 2 supernova. If we have missing hydrogen lines in the spectrum, then we consider the supernova to be type 1, which tells us that little or no hydrogen is left in the debris from the explosion. So that's what defines the difference between type 1 and type 2. Type 2 has hydrogen emission lines, type 1 does not. So let's summarize that idea real quick for type 2 supernova. So here it just shows a typical spectrum of a type 2 supernova, and notice the prominent hydrogen line here. It's a big emission line of hydrogen. So it's a supergiant star with the outer layers intact, right? We know hydrogen will exist on the outside of these types of stars. So if it didn't lose that hydrogen layer, we will get a type 2 supernova. But not all stars keep that hydrogen layer because of the immense energy production and loss of gases. So let's take a look at that. Type 1 supernova are further divided into three important subclasses. Type 1a supernova, which is what I studied in my studies when I was in school, they have spectra that include a strong absorption of silicon. Type 1b and type 1c supernovae lack the ionized silicon line. So it's hydrogen emission that separates 2 from 1, but it's absorption of silicon that separates 1a from 1b and 1c. The difference between 1b and 1c is that the spectra of type 1b supernova have a strong helium absorption line, but 1c does not. So it might be a little confusing to kind of get the hang of these different types of supernovae just based on these different elements. But with some practice and experience, it shouldn't be too much of a trouble. Astronomers suggest that type 1b and 1c supernova are caused by core collapse and dying massive stars, just like the type 2 supernova. The difference is that the progenitor star of type 1b and 1c supernova have been stripped of their outer layers before they explode. A star can lose its outer layers because of a strong solar wind, or, if it's part of a close binary system where two stars are close to one another, by transferring mass to the other star. If enough mass remains for the star's core to collapse, the star dies as a type 1b supernova. Because the outer layers of hydrogen are absent, the supernova spectrum exhibits no hydrogen lines, but many helium lines. Type 1c supernova have apparently undergone even more mass loss prior to the explosion. Their spectra show that they have lost much of their helium as well as their hydrogen. So this just shows what those two spectra would be like. So type 1b, 1c, and type 2 are almost all the same. The only difference is type 2 supernova never lost any of their outer layers, at least not entirely. Type 1b lost their most outer layer of hydrogen, and then type 1c lost the hydrogen and the helium layers at the outside of the star. So they all have the same general process, it's just based on whether or not they have helium or hydrogen layers or both. So that means that type 1a supernova are the real different ones. Type 1a supernovae are not the death throes of massive supergiant stars. Instead, type 1a supernova are thought to result from the thermonuclear explosion of a white dwarf star. Recall that thermo in thermonuclear indicates that high-speed collisions are taking place at very high temperatures to fuse atoms together. Furthermore, a supernova resulting from this rapid release of energy is called a thermonuclear supernova. As we will see, a thermonuclear supernova begins with a white dwarf. This may seem contradictory because we saw previously that white dwarf stars have no nuclear reactions going on in their interiors. But these reactions can occur if a carbon-oxygen-rich white dwarf gains mass, if it's part of a close binary system. So white dwarfs just end their lives as white dwarfs. They never reach that Chandrasekhar limit of 1.4 solar masses. But if they are really close to another star, enough so that they can pull material off of that star and onto the white dwarf, well then it will approach that mass limit. Stage 1 in this figure shows a close binary system in which both stars have a mass of less than 4 solar masses. The more massive star on the left evolves more rapidly than the less massive companion and eventually becomes a white dwarf. As the companion evolves, its outer layers expand, it overflows its Roche lobe, which is an imaginary surface around the star that matter within is gravitationally bound to the star, and dumps gas from its outer layers onto the white dwarf. So the more massive star evolves more quickly, as we have learned, and it becomes a white dwarf. The companion star is now evolving and it expands, but it expands beyond the reach of gravity holding material onto the star, so that material is free to effectively fall off and onto the white dwarf. When the total mass of the white dwarf approaches the Chandrasekhar limit of 1.4 solar masses, the more massive star on the left evolves more I just reread something, sorry. Where am I? When the total mass of the white dwarf approaches the Chandrasekhar limit of 1.4 solar masses, the increased pressure applied to the white dwarf's interior causes carbon fusion to begin there. Hence, the interior temperature of the white dwarf increases. The increased temperature just makes the reactions proceed at an ever faster rate, in a catastrophic runaway process reminiscent of the helium flash in low-mass stars. The reaction spreads rapidly outward from the white dwarf center, with its leading edge, called a flame front, being propelled by convection and turbulence, in a manner analogous to what happens to the shockwave in a core collapse supernova. Within seconds, the white dwarf blows apart, dispersing 100% of its mass into space. Before exploding, the white dwarf contained primarily carbon and oxygen and almost no hydrogen or helium, which explains the absence of hydrogen and helium lines in the spectrum of the resulting supernova. Silicon, however, is a byproduct of the carbon-fusing reaction and gives rise to the silicon absorption line characteristics that are specific to Type 1a supernova. So you can see that silicon absorption line right here, very prominent, and it's only found in Type 1a supernova. Now, that was one way that Type 1a supernova can occur. Another possible mechanism for these types of supernova involves the merger of two white dwarfs, where enough mass is concentrated in the merger to ignite a nuclear explosion. While the initial scenario is quite different than a binary system consisting of a white dwarf and a larger companion star, under certain circumstances, the predicted outcome of merging white dwarfs can be similar. One motivation for this mechanism is that some Type 1a supernova fail to show evidence before or after the event for any large red giant companion. So this could be another way or the way that Type 1a supernovas occur. In fact, this is one of the leading discussions in astrophysics today, is what really causes these things. And these are really the two main theories. And there is a lot of enthusiasm, let's say, behind each one. Personally, I align with the first option, the white dwarf with a red giant companion, but we are still learning, and that's the beauty of science. In addition to the differences in their spectra, different types of supernova can be distinguished by their light curves. All supernovae begin with a sudden rise in brightness that occurs in less than a day. After reaching their peak luminosity, Type 1a, 1b, and 1c supernova settle into a steady, gradual decline in luminosity, like you see by the pinkish line in the figure. By contrast, most Type 2 light curves hang on with a long plateau where they remain at a similar brightness for about 100 days before rapidly fading. For all supernova types, during the period of declining brightness, after the peak, energy comes from the decay of radioactive isotopes. These decays heat the surrounding material enough to emit visible light. So we can also classify supernova based on their light curves, as you can see here. A number of astronomers measure the distance to remote galaxies by looking for Type 1a supernova in the galaxies. This is possible because there is a simple relationship between the rate at which a Type 1a supernova fades away and its peak luminosity. That is, the slower it fades, the greater its luminosity. Hence, by observing how rapidly a distant Type 1a supernova fades, astronomers can determine its peak luminosity, not just its apparent brightness, but its actual intrinsic luminosity at this peak. Then, a measurement of the supernova's peak apparent brightness tells us, via the inverse square law, that tells us the distance to the supernova, and therefore the distance to the supernova's host galaxy. In this way, the Type 1a supernova is being used as what we call a standard candle of known luminosity, and by comparison to its apparent brightness, its distance is determined. The tremendous luminosity of Type 1a supernova allows this method to be used for galaxies more than 1 billion light-years away. Astronomers find the debris of supernova explosions, called supernova remnants, scattered across the sky. The doomed star's outer layers are blasted into space with such violence that they are traveling through interstellar medium at supersonic speeds. As this expanding shell of gas plows through space, it collides with atoms in the interstellar medium, exciting the gas and making it glow. The passage of a supernova remnant through the interstellar medium can trigger the formation of new stars, so the death of a single massive star can cause a host of new stars to be born. So here we have some images of supernova remnants now. On the left we have supernova remnant SNR 0509-67.5, easy to remember. On the right we have the Crab Nebula. On the left here we have N63A, and on the right we have LMC N49. In this image, the red bubble here, we have SNR 0519. I think it might actually be called the red bubble. I'm not sure about that though. Here's one of my favorites. This is the Veil Nebula. And one more. This is Cassiopeia A, or Cass A. So all of these are examples or images of supernova remnants, a star that had exploded. So I'm going to leave you with, I think 2 slides here. This is just an idea of the relics of the fall, and then I'll show you kind of an image showing this. So a supernova remnant may be all that is left after some supernovas explode. But for core collapse supernovas of types 2, 1b, and 1c, the core itself might remain. If there is a relic of the core, it may be either a neutron star or a black hole, depending on the mass of the core and the conditions within which it collapsed. Neutron stars, as the name suggests, are made primarily of neutrons. Black holes, well, you've probably heard of those, and if we have time, we'll get to them. So this is just an image showing all of the possible outcomes of a star formation, or of a star's life. So if a star's mass is below 0.08 solar masses, it can never become hot enough or dense enough in the core for fusion to begin. The result is a failed star known as a brown dwarf. Low mass stars between 0.08 and 0.4 solar masses have convection that dominates the entire interior of the star. So basically, hydrogen is just being converted into helium, and it just keeps continuing and continuing until it just becomes a giant ball of helium. The result is a red dwarf. For intermediate mass stars like our Sun, it will expand into a giant, maybe a supergiant, and then it will exhaust its outer layers in the planetary nebula phase, leaving behind the exposed core as a white dwarf. If we go from 8 to 25 solar masses, you get a supernova that leaves behind the core, some of the core, as a neutron star. But for the true giants out there in space, if you have a star over 25 solar masses, you may end up with what we consider a black hole. Now, for my course, this might be our last video, but I'll still post, hopefully, a video on neutron stars and black holes and some of the more interesting things that are out there, because it gets really weird at that point. But as for always, thanks for watching, and I hope you guys are enjoying this. I might still, again, post a few more lectures beyond this, but we're coming to the end of our course, unfortunately. So let me know, as always, if you have questions, comments, concerns, constructive criticism, anything. I'm open to anything. So take care, guys.